All right, let's take a look at this week's logistic regression analysis assignment. It seemed to work really well with ARIMA, so we're talking about it a little bit early. So your job here was to determine whether driver hair color is associated with different odds of receiving a traffic ticket. So I gave you a file that's a 1% sample, random, of all California drivers who were listed, issued a license during a 1 calendar year period. That's 36,655 persons. So note that there's lots of variables in the file. It's a big old sample size. It's huge. So even tiny things can be statistically significant. That's power. And so let's jump in and see, is hair color associated with your odds of getting a ticket? It'd be kind of stupid if it was, right? But, you know, the real world's full of plenty of stupid examples. So first thing I want you to do is a preliminary univariate analysis. I want you to look at, the idea here is logistic is a new thing. You guys don't know what's going on so much. So let's relate it to something you do know a little better. That is chi-square tests of independence. So here we're going to see if the predictor and the outcome variables are related. So driver hair color is our primary predictor of interest, and ticket status during their 1 year, first year of driving, the outcome variable, are both nominal. So what do we use to look at whether two nominal variables are related to each other? Chi-square test of independence. So to get it, we go to analysis, we go to descriptive statistics, and we go to cross tabs. And just so we all match here, I tell you kind of what to do. So I say, take the outcome variable ticket and move it to the columns box. Bam, there's ticket, columns. Then select the independent variable, the one we care about is hair color, and move that to the rows box. To get the chi-square itself, we have to click statistics, and we click chi-square. And I don't have you getting Kramer's V for whatever reason. We're just messing around here. That's why. But normally you would get Kramer's V. And then under cells, we got to get some stuff as well. So we have to get the percentages. And so one way of figuring out, do I get row or column percents, is think to yourself, for this independent variable, do I have equal numbers of people in all the different hair colors? No. Well, then the only way to fairly compare this is look at the percent within each hair color who got a ticket, right? So we need to do, what variable is hair color? It's row. So we need to get row percentages. So we're also going to get adjusted standardized residuals. Those are those things that are like z-scores, where if they're like 2 or bigger absolute value, it tells you something funky is going on in that cell. Look here to see what's going on. So click continue and then click OK, and we're running our chi-square. So I kind of baby stepped you through this assignment, like to an extreme degree. It's called garden pathing because the prior instructor hadn't done logistic as well. And so when I was guest lecturing in there, I wanted to teach in a way that that instructor could do it as well as you. And so hopefully it doesn't drive you too nuts. It drives some people crazy, but I baby step you through this stuff. So first of all, let me do sort of the overall how I would look at this if I wasn't baby stepping you. I would say, all right, so in the no and yes, and we've got hair color as rows, I'm going to pick yes and look at the percent who got a ticket in their first year of driving by hair color. 7% of gray, white, bald, 6.7% of those with black hair, 15%, 0.2, I guess, of those with brown, 12.1 for red, 14% blonde. Is that statistically, are those differences statistically significant? First table of the chi-square, sig's less than 0.05, yes. So hair color is related to your odds of getting a ticket your first year of driving. That's kind of goofy. So anyway, let's answer the questions. Fill in the yes column percents, column percents here, not column percents here. To 1 decimal, include the sign if present for the adjusted residual. So for gray, white, bald, what percent got a ticket? That's 7.0. Okay, so 7.0%. For black hair drivers, that's 16.7%. So 16.7%. For brown, it's 15.2. For red and auburn, 12.1% of them got a ticket. And for blonde, it was a straight 14.0. So let's also do our adjusted residuals as well. So let's fill those in, including the sign if present. So for that cell, it's negative 9.5, negative 9.5 for gray white bulb. For black, it's positive 5.7. For brown, it's 0.7. Okay. I put the 0 on there. For red and auburn, it's negative 2.3. And for blonde, it's negative 2.1. All right. So let me highlight it and do my little thingy here. So what does this all mean? Good question. Let me center it. So remember, it's statistically significant. So the chi-square tells us there is a relationship between hair color and odds of getting a ticket. Where these things are 2 or bigger, it tells you that cell's funkalicious, and you look at the sign to see if it's negative, it means that cell was lower. If it's positive, like there, sorry, it means that one was higher. So gray-white bald folks were less likely to get a ticket than expected. Black-haired folks were more likely to get tickets. Brown-haired folks, not 2 or bigger, so they got a ticket about as much as you'd expect if hair color wasn't associated with your odds of getting a ticket. Red, auburn, and blonde, lower odds of getting a ticket. So let's fill this stuff in. Put the appropriate percentage of the blanks and circle the option. The percentage of drivers with black hair who receive tickets is, black hair is 16.7%. Let me do my little thing so we can actually read this stuff. Who received tickets was lower or higher? What do we say? Do we pick lower or higher? Well, 16.7 was associated with a adjusted standardized residual that's positive 2 or bigger, so they were higher. There was more black hair drivers who got tickets than expected, so we're going to highlight higher. And I need to save this as the key before I forget to do so, because no doubt I will. Key. All right, and let me put that up here too. So we are ready. Key. Bold, highlight, give. All right. So they're more likely to get a ticket, right? There's 16% versus 7. These guys are about the same, 12 and 14. So they're more likely to get a ticket than one would expect if hair color and being ticketed were not associated, be less than 4 to 5. On the other hand, the percentage of drivers with blonde, so let's put that in here, it's 14.0. Red auburn, they are 12.1% of them got tickets, and particularly gray white bald, which is 7. Geez, they didn't get a lot of tickets. And let me highlight them again just so they stand out to y'all. And I'm just copying the percentages from above, which confuses people. I was trying to help, I swear, and I made some things worse for some people. All right, received tickets. So are they lower or higher? Were they more likely or less likely to get tickets than would be the case? Well, their adjusted residuals are negative, right? 2 or bigger in negative. So they're less likely, negative, less likely to get tickets than would have been expected if hair color and getting a ticket were not actually related. So lower. Drivers with brown hair received about as many tickets. So I'm trying to teach you, what do you do with this one that wasn't significant? So they were 15.2%. And the fact that their adjusted standardized residual wasn't absolute value of 2 or bigger just tells you, yeah, they didn't differ from expectation. So if hair color and getting a ticket were not associated, you'd expect about 15.2% of brown hair drivers to get tickets. So that is how you answer that piece. So this is a really weird finding. Why would you find that, hair color is associated with their odds of getting a ticket? Could this be confounding by driver age? Could be, right? Because who has gray, white, bald hair? Older people, they're less likely to get tickets. Could it be, so why do red, or sorry, so that might be why they're lower, right? 7%. But what's with the red, auburn, and the blonde? Why are they less likely to get tickets? So could it be confounding by sex, perchance? Like if you get your hair colored, are you more likely to get red, auburn, or blonde? Could be. So maybe it's confounding by sex that makes it look like these variables are related. It's just age and sex confounding. Who knows? But we're going to test it eventually. So we're going to eventually do an analysis where we remove differences in your odds of getting a ticket associated with age and associated with sex, and then still see is hair color associated with your odds of getting a ticket. Okay, but the first thing we're going to do is a crude logistic regression analysis. So let's do that. So just like in the lecture, we did a chi-square. Now we're going to do a crude logistic regression to see what's going on. So to do this, we go to analyze, we go down to regression, but now we go to binary logistic. And in binary logistic, we need to move our dependent variable or outcome variable, that is ticket, to the dependent box, and it's going to predict the odds of the level that's coded as 1, right? Then we select our independent variable, that's hair color, boom. We move that to the covariates box. And hair color is a categorical variable. So we have to tell SPSS to make dummy variables, right? So let's do that. So we click categorical, we take hair color, we scooch it over, and note the default's last. Do we want last to be the variable we compare things to? Well, last I think is blonde, right? So we'd be comparing the odds of everyone getting a ticket compared to blondes. I think a better one is first level, which is 0, which was gray, white, bald. Remember, they're the lowest. So we're going to change this to first. And we're going to click change. And that's going to mean that all the other hair colors are compared to gray, white, bald. Okay. And you got to trust me on this. It means that because they were the lowest, the odds ratios for the other groups are going to be positive and or greater than 1. And those tend to be easier for students to interpret. So anyway, it's another reason to compare to gray, white, bald is it's easier because the odds ratio, all the other groups are higher than 7%, right? So trust me on that one. All right, click OK. Under the regression output section, oh, that's it. We don't pick any options or anything. That's kind of boring. All right, well, click OK. So we get our logistic regression analysis, and I tell you a couple things you can poke around. So first of all, the overall model to tell you if this model significantly predicts the odds of getting a ticket is not block 0. Remember, you ignore block 0. All this stuff under heading block 0, ignore this. We want to go to block 1, enter. So note here, we get this omnibus test of coefficients. There's one called model. Model is the last row, sig's less than 0.05. That tells us overall, this model that includes hair color significantly does significantly predict your odds of getting a ticket your first year of driving. Your R squared is teeny tiny, 0.006. It's really small. You get a classification table. And then we get the variables in the equation. So how many categories of hair color were there in the crosstab? I don't know. There's 1, 2, 3, 4, 5. So our answer here is 5. And for some reason, this really confuses people. I'm just trying to baby step you. How many dummy variables are used to represent hair color in the variables in equation table? I don't know. Let's look. Okay, hair color. This one right here is not a dummy. This is that omnibus test, right? So do not count this one. This tells you overall, does hair color predict your odds getting a ticket? Sure as hell does. But anyway, these are your dummies, 1, 2, 3, and 4. They represent the different hair colors, okay? So I guess the end, that's 1, 2, 3, 4. So the answer to this one is 4. How many dummy variables did SPSS use? K-1, that is total number of hair colors minus 1. So 5 minus 1 is 4. So 5 is the wrong answer. I tell you, for number 4. And then you're supposed to fill in which category is represented by each dummy variable. That is dummy variable 1, 2, 3, or 4. I just want you to write what color. So I'm trying to get you using this table up here called categoricals, variables, codings. Categorical variables, codings, that's literally what it's called. And note that for hair color, there's 1, 2, 3, 4. And the level that's coded 1 for each one of these is what is represented by that dummy variable. So black is represented by dummy variable 1. So where it says hair color 1, that's folks who have black hair. Hair color dummy 2, that's browns. That's folks who have brown hair. Dummy variable 3, which group's coded 1, red/auburn. So red/auburn. And finally, dummy variable 4 is blondes. Blonde. All right. Those are the levels that are represented by the 4 dummy variables. So which hair color is not represented by a dummy variable? Well, it's going to be the one that is zeros across all the dummy variables, and we did first, right? So it is gray, white, bald. So the answer here is gray/white/bald. That is our referent. All the others are compared to folks who have gray, white, and bald hair. All right. Under logistic regression, blah, 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 variables and equation. I'm just telling you what's in the table here. These are your odds ratios. Make sure they're significant. So we want the odds ratio. I've filled in the referent here so you don't accidentally fill it in. For gray, white, bald, it's 1. Okay, it just is. That's the way we represent the referent variable. They're 1. You don't get a sig. They're not 1, 2, 3, or 4, so you don't get a sig value. But we do get an odds ratio and a sig for black, brown, red, auburn, and blonde, right? What I suggest you actually do here is change these labels to the color represented, black, brown, red, auburn, or blonde, so that this starts making a little bit of sense to you. So again, this is the Omnibus test overall, whether hair colors does significantly predict your odds of getting a ticket. So don't do that one. That doesn't have a parentheses number. Start with hair color 1. Hair color 1 represents black hair drivers. Oops, didn't like that very much, did it? Black hair drivers. Hair color 2 is brown hair drivers. Hair color 3 is red/auburn. And hair color 4 is blonde. All right, why did I have you do that? Because it makes this thing more interpretable rather than dummy 1, dummy 2, right? My goal is to help you interpret these things. All right, so now we want the odds ratio to 2 decimals and also indicate if the sig value is less than 0.05 in this column, and that's a yes or no. So for black hair, odds ratio is 2.644, so to 2 decimals is 2.64. Is the sig less than 0.05? Yes, it sure is. How about brown? Brown is 2.37. And is that sig less than 0.05? Yes, it is. Red auburn is 1.82 is what we'd round that to. Sig less than 0.05, indeed it is. And finally, blonde, 3.15, and sig is indeed less than 0.05. So every single one of these hair colors had higher odds of crashing, right? Because these odds ratios are greater than 1 and significant than those who are gray, white, bald. So yeah, so everyone, and again, this is probably old people, right? So younger people have higher odds of crashing than gray, white, bald-headed people. That's what this tells us. So let's do number 8. So fill in the following table. Use the percentage difference formula, which is odds ratio minus 1 times 100, and round to whole numbers. All right, so the odds of black-haired drivers being ticketed were, let's see, we're going to round this percentage difference. So we take 2.64 minus 1 would be 1.64 times 100 is 164%. And they are higher odds of crashing because that's an odds ratio that is greater than 1. So they had way higher odds of crashing compared to gray, white, bald-headed drivers. All right. Then drivers with gray, white, bald hair, blah, blah, blah. Similarly, the odds of being ticketed for brown-haired drivers. And so let's fill that in again using this little formula. Brown is 2.37 minus 1 is 1.37 times 100 is 137%. Wow. And again, it's going to be higher when we finally get there. Red Auburn is 1.82 minus 1 times 100 is 82%. 82%. Boom, boom. And blonde-haired drivers, there are 2.15 minus 1 is 1.15 times 100 is 115%. And all of these odds ratios, right? All these odds ratios are greater than 1 and significant, so they are higher odds of getting a ticket than grandmas and grandpas. All right, so everyone's got higher odds of getting a ticket than grandmas and grandpas, right? So compare these to what you filled in earlier for the crosstab. They do seem different, right? So the crosstab found an overrepresentation of tickets among black-haired drivers, underrepresentation among blonde, red Auburn, and gray, white, bald, right? So why are things different here? Things are different here because we're no longer comparing this compared whether getting a ticket and hair color were independent, right? That's chi-square test of independence. And found no, these guys, gray, white, balds, less likely to get a ticket, black is more likely to get a ticket, brown didn't differ, red Auburn was lower odds of getting, or less likely to get a ticket, sorry, and blonde was less likely to get a ticket. So why are these all higher? Well, it's because we're comparing each one of these, black, brown, red, Auburn, to this group, the gray, white, bald. They were least likely to get a ticket. They were 7%, only 7% of them got a ticket. Every other group, 16.7, 15.2, 12.1, 14, were all way higher odds of getting a ticket, right? That's why the results differ here. We're no longer doing a straight all hair colors comparison to their likelihood of getting a ticket. We're comparing everyone to one of the groups, the reference group, that is gray, white, bald. So compared to gray, white, bald, yeah, everyone's more likely to get a damn ticket. So this is weird. So let's run what we call an adjusted logistic regression analysis, where we adjust for, age, we'll adjust for sex. Maybe that's why we're finding this weird relationship between hair color and your odds of getting a ticket. Maybe it's just confounding again. It's like Scooby-Doo. Once again, it's confounding. So we go into regression and we go into binary logistic, and I tell you right here, select your covariate predictor variables, sex and age, and move them both to block 1 of 1 box, this box right here. They kind of renamed it here, in case you didn't notice. It was called covariates before. Do not change anything about hair color. So note that age is a continuous variable, so we do not need to make it dummy variables for age. Do not make dummy variables for age. You'll be very sad and get a lot of output that's very confusing. However, sex is categorical, so we need to tell SPSS to make dummy variable for sex. Well, there's only 2 levels, so number of levels minus 1 is 1 dummy variable. So we click categorical. We take sex, we move it to the categorical box. And again, do we want last or do we want first? Well, how was it coded? Click categorical, blah, blah, blah. All right, so we want female coded as 0 to be the reference level, since males coded as 1 tend to have higher tickets rates. So female coded 0 wouldn't be last, it would be first to make them the referent. Make sure you hit change. We're going to do sex, and it's going to compare all levels to first. The only other level is male. First is female. Click continue. All right, change the reference category to first, blah, blah, blah. Don't do anything with hair color, and click OK. We now have, instead of a crude logistic, we have a logistic that is adjusted for age and sex. And I will not skip to the fun part. Under the logistic output section called block 1 method. So again, you got this block 0 thing. Ignore all this crap for step 0. Go here to block 1. Okay. In the variables in the equation table, that's right here. Change each dummy variable to the name of the hair color level represented by that dummy variable based on the categorical variables codings. So again, just kind of looking up here at categoricals variables codings, dummy variable 1 for hair is black, dummy variable 2 is brown, dummy variable 3 is red auburn, and dummy variable 4 is blonde. So I'm telling you to change those here. Do not change this first one, which is an omnibus test that tells you whether hair color overall is associated with your odds of getting a ticket. And the answer is no. We want to change hair color friends 1, 2, 3, and 4 to actual hair color, so it makes more sense. So again, this first one was black hair, right? Black hair compared to gray, white, bald. This next one is brown hair. This next one is red/auburn. Oops, auburn. And the final one is blonde. All right. And again, you don't have to do that, except that I ask you to because it makes more sense when you're looking at the output to understand it. So we can also do that for sex as well if we want to. We could say that this is male. I don't think it hurts to do that. Do I say sex read by the dummy variable? I do tell you to do it here, so I'll wait till we get there. So black hair, we want to know the odds of black-haired people getting a ticket relative to gray, white, bald, and we want to know if it's SIG or not, so we put a yes or no here. So for black, the odds ratio to 2 decimals is 1.09, so 1.09. Is it statistically significant? Negatory, so no. Black hair drivers do not have different odds of getting a ticket compared to gray, white, bald hair drivers after adjusting for age and sex. How about brown? Was 1.08. Significant? No. 0.461 is not less than 0.05, so no. Red auburn, 1.02. That's really close to 1. So is that significant? Nope. Also not significant. And finally, blonde, 1.0, we'll round that to 5, right? So 1.05. And SIG, no, it's not less than 0.05, so no. All right. So what happened? I don't know. I asked you that at number 12, actually. But anyway, there's your odds ratios. And note that the overall omnibus test tells you hair color overall is not associated with your odds of getting a ticket anymore. In this model, we've adjusted for age and sex. So for number 10, we're also going to look at sex, and then 11 is going to be age, just interpreting those as well. So for sex, the odds ratio, or first of all, I tell you, change so we know what sex dummy code 1 equals. Going up top, find categorical variable codings. Sex, female and male, find which one's coded as 1, because that's what's represented by that dummy variable. It's male, right? See that? So it is male. So let's go ahead and change sex 1 to male so that it makes more sense. So males compared to females. So males compared to females had a odds ratio of 1.77. And was that significant? Yep, sure was, less than 0.05. So that one was statistically significant. So males were more likely to get a ticket than females. How do I know that? The odds ratio is greater than 1. So if you do that little formula, 1.77, actually, we're going to do that later. So I won't do that yet. So for age is also in here. It's got an odds ratio of 0.973. So let's put that in here to 2 decimals, 0.97. And is it significant? It sure is. So it gets a yes, that is statistically significant. So age is significantly associated with your odds of getting a ticket, even after adjusting for sex, I guess, and and hair color. So is hair color, number 12, still associated with the odds of being ticketed after adjusting for the fact that drivers with different hair colors also differ in their age and sex distributions? No, it's not. So that's the short answer. No. So it was right before, but now that we've adjusted for age and sex, we are finding that hair color is not actually associated with your odds of getting a ticket. So what information did you lead to reach that conclusion? Well, there's two ways to answer this. The way I hoped you answered is this Omnibus test up here for hair color, the one that has no EXPB. SIG's not less than 0.05. So I was kind of hoping you guys would say hair color Omnibus test. That would make your professor very happy if you answered that. But there is another way that works as well. So again, for those at home, this was the one that didn't have a little parentheses after it or a parentheses number after it. It doesn't have an EXPB. This is a test across all of the hair color dummy variables. Is hair color significantly associated with your odds of getting a ticket? SIG is greater than 0.05, so the answer is no. The other way to answer this, if you didn't use the Omnibus one, is look at each individual odds ratio, and if none of them are less than 0.05, then your hair color wasn't associated with different odds of getting a ticket. So black, nope. Brown, nope. Red auburn, nope. Blonde, nope. So that's the other way you could have answered it, is looking at the individual SIG tests for each dummy variable. So what do you think happened to change the conclusion from the Crude logistic regression analysis? Well, what did we do? We adjusted for age and we adjusted for sex, and suddenly hair color is not associated with different odds of getting a ticket, right? So what do I think happened? I think the original analysis was confounded by age and, I guess I did sex and age, making it look like hair color was related to odds of being ticketed. Once we adjusted for that, no relationship, right? So boom, something like that. That is what happens. So it looked like they were related. We adjusted for these confounders and voila, no longer related. So fill in the following blanks with percentage differences using either the formula OR minus 1 times 100, that's for odds ratios greater than 1, or 1 minus OR times 100 for the odds ratios less than 1. All right, so the odds of female drivers, or excuse me, the odds of male drivers being ticketed were, all right, let's go here. 1.77 is that thing rounded, right? So minus 1 times 100 is 77%. So they were 77%, the males. And is it lower or higher? How do we know that? Well, the odds ratio is greater than 1, so it's higher. So males were, this is like not shocking if you do traffic safety research, 77% higher odds of getting a ticket their first year than female drivers. So what about the age one? So for age, we had an odds ratio, we rounded this to 0.97 up here, right? And it was significant. So that is a odds ratio that's less than 1. So we're going to use this formula, 1 minus the odds ratio times 100. So 1 minus 0.97 is 0.03 times 100 is 3%. So 3% is what goes in here. So 3, and I guess, yeah, maybe good enough. 3%. And is it lower or higher? Well, that odds ratio is less than 1, so it's lower. So for every year older you were, your odds of getting a ticket during your first year were 3% lower. And that's kind of it. So on the APA write-up, a couple things that might have been, let me save this sucker, might have been a little bit confusing. First thing that's confusing is actually, no, this wasn't confusing. You did have to get these from your chi-square. So again, they are your row percents. So hopefully you got the row percents and you filled that in. What else is confusing? You had BMI. This is your crude analysis. So this would be your hair colors. This would say hair color, and this would be gray, white, bald, black, brown, red, auburn, and you have to add another row for what is it, blonde? So you can copy, paste to get another row in here, right? That is a way you can get another row in your table, and then you could add your blonde. Constant is just this constant one. Just fill in the stuff, what it asks for, 1.14, negative, standard error, 0.12. Gets a star on the 1.7, 1.14. That's it. So this Nagelkirky thingy right here, this comes from up here at your your chi-square thingy with your Nagelkirky, sorry, comes from your Omnibus test of model coefficients. You should have said a chi-square with, it's not 3, it's 6 degrees of freedom. Is n is equal to still 36655. That's the total sample size. And your chi-square is 1170.37. Your p was less than 0.05. Your Nagelkirky is right here. It's 0.06. And I think this stuff is pretty straightforward. It's basically the same, except you got to add another row for blonde again. So you can copy, paste to get another row in there. So you can fill in blonde and your other, hair colors. I think the rest was pretty straightforward. If you have any questions, of course, hit me up in the chat. And otherwise, good luck.